Good day! With this episode, we begin a new course devoted to the selected chapters of quantum mechanics. My name is Timur Galimzaynov. I am a researcher at the Theoretical Physics and Quantum Technologies Department of National University of Science and Technologies. This course will be presented by researchers and professors of our department. I will be with you during 2 lectures. This episode is the beginning of the first one, devoted to the basis of quantum mechanics. The beginning of the 20th century is the age of the great revolutions and upheavals in human civilization. 2 of them turned over people's conceptions on the world structure. The first one is the theory of relativity, which showed that the space and time, the world we live at, is not what it looks like. The space, which is the very fabric of our world, can be deformed. The march of time, which is the very base of our existence, can be varied. The second one, quantum mechanics, showed that all laws that we knew doesn't work properly in the micro world. It discovered a whole new bunch of phenomena that contradicted to people's understanding of the world and so-called common sense. Particles in micro world, roughly speaking, can be in several spaces simultaneously and pass through the walls. Our course is devoted to the second theory, quantum mechanics. In the first lecture, I'll give you a short introduction into history of quantum theory. As any revolution, it had not occurred instantly. It took several decades to collect various experimental results that could not be explained by old theories. The only way out was to develop a new theory. It took about 10 years or more. In the 17th and 18th centuries, Robert Hooke, Christian Huygens, and Leonhard Euler proposed a wave theory of light, based on the experimental observation of light diffraction and interference. From this time, scientists divided all physical phenomena on the wave-like, which display diffraction and interference phenomena, and particle-like, which obey classical mechanics laws. In 1895, Wilhelm Röntgen discovered X-rays. However, he could not determine their nature, whether it was wave-like or particle-like. Later, due to diffraction, it was shown that X-rays had wave nature, but were not particles. However, that conclusion contradicted to the extremely low rate of ionization of gases by X-rays. To remove this contradiction, the assumption of mysterious granularity of the X-rays wavefront was needed. At the other battlefront, at 1859, the problem of black body radiation was stated. Classical equation described it up to the infrared frequencies. But at high ultraviolet frequencies, theory diverged with experiment. Moreover, the theory predicted infinite power of black body radiation. That situation was called ultraviolet catastrophe and was a huge problem. To solve this problem, Max Planck utilized Boltzmann's idea and suggested that light is radiated by some portions, quants, the energy of which is proportional to the light frequency. The new equation contained new fundamental constant, later called Planck Constant. The funny thing was that energy quants were intended as a mathematical trick. Planck was going to take a limit of 0 portions, but there were no need in that, as the results was right without this limit, and brought to the excellent match with the experiment. However, the nature of the quants were unknown. At the same time, the photoelectric effect was discovered. The light can knock out the electrons from the surface of the metal. The strange thing was that at high frequencies of the light, whatever low intensity you use, the effect conserves, while at low frequencies, there is no effect whatever high intensity you use. So, only photons of high frequencies could knock out the electrons, regardless of the intensity. Albert Einstein explained that phenomenon by quantum nature of light. Light is observed by finite energy portions proportional to its frequency. The other mystery was the atom structure. It revealed a discrete spectral series of the atom, which could not be explained in the framework of the classical physics and was attributed to some planetary atom structure. However, from the point of view of the classical electrodynamic, planetary model leads to high instability of the atoms due to the dipole radiation. That all brings to the strange unexplained stationary model of the atom. From the other side, true particles, electrons, showed some evidence of their wave nature by diffraction of the crystals. It was predicted by de Broglie that all particles can be considered as waves with wavelength inversely proportional to their momentum. That was the other side of quantum revolution. So, you can see that at the beginning of the 20th century, all premises for the new theory were revealed. Strange quants were needed to explain the physical phenomena. Light waves should be considered as particles. True particles were no more particles but should be considered as waves. All these brought to two new theories: matrix mechanics, developed by Heisenberg at 1925, and wave mechanics, developed by Erwin Schrödinger at 1926. The first one explained all experimental results on the quantum nature of light and structure of atom spectral series. The second theory explained particle diffractions and showed that particles in the microworld should be considered as waves. Several months later, Schrödinger showed the equivalence of the matrix and wave mechanics, basing on the conception of the matter waves. That can be considered as the beginning of contemporary quantum mechanics. From this point, we can move to the study of this theory. So, in the next episode, we'll begin with the discussion of the properties of the matter waves and conclusions that we can derive from this conception.